Consider the pulley system below. So we have M1, which rests on a rough surface with a mu, and I'm going to assume this is kinetic coefficient of friction of 2/3. M2 is free hanging 10 meters above the ground level. So I'm going to assume that this right here is 10 meters. So now we want to redraw the diagram above, including all forces. Okay, so to do that, we would say that this would be, I gotta change colors. Change colors, blue. Hopefully there's going to be enough contrast. And there's enough. So this will be tension. This will be force, gravity. And here we're going to have a force, tension, pulling. And in this direction we're going to have a force, no, not force, gravity. Force, friction, opposing direction of motion. And I'm going to assume it goes this way because we have the force of gravity pulling down on M2. All right. So that's the general idea for part 1. Part 2, given the system is released from rest, calculate the acceleration of M1. Okay, so here's the key idea here. This is kind of the heart of the problem. So we're going to assume that these are connected by a taut string. There's no slack in it, and it doesn't stretch either. And so the acceleration of M1 is going to be the same as the acceleration of M2. Though the acceleration of M2 is going to be down, and this one is going to be horizontal. The magnitude will be the same. And there's basically two ways to approach these problems. The correct way and better way is to map out the free body diagrams. Here you have gravity and tension. Here you'll have gravity and tension. And you write an equation where the sum of all forces, that's supposed to be sigma, equals force equals mass times acceleration. And so for M2, you're going to have force, gravity. I'm going to consider down the positive direction, minus tension. And then the sum of all forces on 1 is still going to be also going to be mass times acceleration. This would be mass 2 though, and this would be mass 1. But the accelerations will be the same. And that's going to be tension minus force, friction. In this case, tension is going to be overcoming friction, causing the motion to go to the right. You set the t, you solve for t, you set the t's equal to each other, and you solve it. That's the correct, better way of doing it. The quicker way of doing it is we have the sum of all forces equals mass times acceleration. Well, I can kind of sort of say the sum of all forces is going to be the sum of all masses times acceleration. Now, this sum of all masses, it's kind of flaky, but it's going to work great here. So all the forces at play here, I'm going to ignore tension, and I'm just going to look at the forces that are causing motion, that's moving this. And so we're going to have force, gravity, which I'm going to call mass 2 times gravity, and it's going to be opposed by friction. So force of friction is going to be the coefficient of friction times the normal force. In this case, it's going to be mass times gravity, specifically mass 1 times gravity. If this was on an incline, it'd be different. We'd throw in a little cosine theta here, but you could say that, well, this angle here, theta is 0. You know, kind of like this. If you look at an incline, multiply by cosine of it. Don't get hung up on that. Mg, just mass times gravity. Okay. So this can be minus mu mass 1 times gravity. And that's the sum of all forces that are going to be causing motion. The masses are going to be mass 1 and mass 2, and they will move together. And this will produce an acceleration that's common to both of them. Okay, so now, red. We're going to solve this for acceleration. So acceleration equals mass. I'm going to factor out the gravity. Yes, gravity times mass 2 minus mu, which we know is 2/3, mass 1, all over mass 1 plus mass 2. And this is going to give us 9.8. Yes, 9.8. Or can I round that up to 10? I'm rounding that up to 10. Convenience. 10. Mass 2, which is 100, minus 2/3 of M1. Ooh, this is really convenient. Which we know that M1 is 75. all over the sum of mass 1 plus mass 2, which is 175. So this is going to give us 10 times 100 minus 50, which is itself 50, over 175. This top part will be 50 times 10, which is 500, all over 175, which is going to be, I should be able to know this. All right, calculator time. Boom, clear, 500 divided by 175. Come on, whole number. Nope, 2.86. 2.86 meters per second squared. And one key thing to note here is it is less than 9.8 meters per second. So if we got a number that was bigger than gravity, we would know that we did something obviously wrong. At this point, we only, might have done something wrong, but it was not obvious. So that's going to be the acceleration of m2, which will be the same thing as, so we found the acceleration of m1, which is the same as acceleration of m2. So check and check. Bam, bam. Find the tension of the string. I'm not going to do that. We basically take this formula, plug in values. We could do that. I don't want to do it. So number 5, calculate the velocity of m2 when it strikes the ground. All right. So when it strikes the ground, so we're going to use our kinematic equations here. So this is going to be an acceleration, I'm going to assume, is constant. That's what I mean by a equals a. Then we integrate both sides with respect to t, and we get at plus v naught. That's our second kinematic equation. And then integrate with respect to time one more time. We get 1/2 at squared plus v naught t plus x naught. And we want to calculate the velocity of m2 when it strikes the ground. All right. So there's kind of a super secret fourth kinematic equation. And basically, we solve this for time. We plug that into this, and we get another equation. That equation, you might recognize, is v final squared equals v initial squared plus 2a delta x, where delta x is the distance traveled. So let's see. Calculate the velocity of m2 when it strikes the ground. So v initial is going to be 0. And 2, well, it's just going to be 2. We know our acceleration is 2.86. 2.86. And we know the distance traveled is going to be 5. It's going to fall 5 meters. So this will be 5. And so 2 times 5 is 10. 10 times 2.86 is 28.6. You might be like, 28.6 meters per second. No, this is meters squared per second squared because it's v final squared. And therefore, the v final is going to be this number times 10 second square root, second answer, and we get about 5.34. I'm going to round down a little bit just because I used 10 up there. I know. Not the proper way to round. I'm like, well, maybe I'll just try and make offsetting mistakes. Probably not a best practice, but sometimes kind of sort of works. So from here then, we're going to say that that's the velocity of m2 as it strikes the ground. How long will it take for m2 to strike the ground? So for this one, we already know the speed it's going to strike the ground with, so we can use this equation. We could also have used this one to find the time. Either way works. So t equals v final, this right here is v final, minus v initial all over acceleration. V final we know is 5.34. V initial is 0 because it starts at rest. And our acceleration is 2.86 over 2.86. And we get something like 2 seconds divided by 2.86. 1.87 seconds. Excellent. So calculate how long it takes for m2 to strike the ground. 1.87 seconds. Calculate the new acceleration of m1 after m2 hits the ground. Okay, so the point of this question is once the m2 hits the ground, it's no longer going to provide tension pulling m1. So this is m1, and initially we have tension pulling this way and force friction pulling that way. Well, once m2 hits the ground, this part disappears. And so we have a new, basically, acceleration. So force equals ma. Acceleration will then be force divided by mass, specifically mass 1. And m1, so the force is going to be due to force friction. And so this is going to be mu, the normal force is going to be mass 1 times gravity divided by mass 1. And therefore this is going to be mu, which is 2/3, cancel the m's, times gravity, which is going to be 2 divided by 3 times 9.8. I know I used 10 before. Probably should stick with that. I'm not going to. About 6.5 meters per second squared is how quickly it's going to decelerate. So then, calculate got the new acceleration. How much further will it travel after M2 hits the ground? Okay, so now, since these are connected by a taut string, is tight and taut the same? Maybe in this case. That's okay, we're not going to focus on that. We know the speed of M2 is going to be the same as M1 the whole time, because they're connected by a string. And therefore, I'm going to assume that V initial for mass 1, when mass 2 hits the ground, is going to be 5.34 meters per second, just like up here. And so we're now going to use this kinematic equation right here. We want to find the distance traveled, which will be x. I'm going to call it x final. 1/2 times, we don't care about the time. Actually, I'm going to use this equation instead. The way we could do it before is we could solve this for time to find out how long it travels, and we plug it in to that equation. This one just keeps us from having to solve for time. If it asks us how much longer it travels, then we would use this equation. But since we have further, we're going to use this one. So I'm going to say that delta x, which is how much further it travels, and since x initial we're going to assume is 0, basically it's just how far it travels, will be v final squared minus v initial squared all over 2a. And you might think, oh, we're going to get a negative number here. Not quite. I don't think so. So v final it comes to a stop. So it'll be 0 minus initial, which is 5.34 squared, all over 2 times the acceleration. And I wrote this as 6.5 meters per second squared. What I should have written was negative 6.5 meters per second squared. The squared is on the seconds. The 6.5 is negative. So the negatives cancel, and we get 5.34, nope, got the point, 0.34 squared divided by 2 divided by 6.5, and I get 2.19 seconds. So for the M1 will continue moving on for 2.19 seconds until it comes to a complete. Oh no, that's not seconds. Sorry, my mistake. Meters. It'll continue traveling for 2.19 meters, at which point it'll come to a stop and no longer travel. So that's how I approach this problem. Hope it helped. See you next time.